Hello and welcome back to Engineering 201 Electrical Fundamentals. And I wanted to go back to something that I mentioned in the last lecture. If you go back to page 3 of the last lecture, I think I'd put this expression up for the addition of complex numbers if they were in rectangular form, and I said that you could subtract them just as easily, and I believe that I put a negative sign there and then I put a negative sign here, which then is not true. That would not be true. It would rather be equal to, if I've got a plus or minus this, a plus jb plus or minus this, I really need to say that it's a, then plus or minus the c term, and then I'm going to have plus j times b, or excuse me, j with b, then plus or minus the d term. So obviously an important difference, but a slight difference. It was certainly correct when I had the addition in there, and I just casually mentioned the subtraction and put that subtraction in the wrong spot. So be careful of that. Go back, if you would, and correct your notes. If you printed out the PDFs, you may want to correct that also. So let me double check that now. And got the plus or minus from there. Yes, now we're good with that. Great. So just wanted to point that out so your notes would be complete and correct. Well, speaking of last time, I think we had finished up with this problem. This was the last problem that we did. We were given that we had some voltage across an inductor of 1 millihenry, and we were looking for the current, and we went through this, and some of you might have said, well, this seems like an awful lot of work, but remember that if we have something, we'll add a little something in here. If you have a circuit that looks like this, there's our voltage source and our inductor. I'm going to say that this is V of t, and this is L. We could say, if we were to look at Kirchhoff's voltage law, that V of t minus then L, so that's the gain. Just starting here, I'd have gain through there, and then I'd have drop through the inductor. The drop through the inductor is given by the expression L times di dt, or of course we have the I right there, okay, and that's equal to 0 by Kirchhoff's law. So we could go ahead and solve for the current here if we wanted to. We'd have to go through that calculus problem and sort that all out. So when you look at it in that context, and of course it'd be a calculus problem with this as one of the functions. So when you look at that, then our methodology of using phasors seems more and more attractive. Well, going back to this one, and we'll pick up on a new problem in just a moment here, but going back to this one, I wanted to look at it in terms of phasor diagrams and whatnot. If we look at it in the time domain, we would have had a couple of waves like that. But I want to look at it in terms in more detail in the phasor domain. So this is the real and then the imaginary. I'll put the imaginary, it should be a G, but I'll put a J so we know that that's the J direction, the complex direction. And then again, this is phasor. And looking at it in phasor, we have the voltage, which is, what do we say? There's the voltage phasor. 5 at minus 180. Okay, so here is our voltage. We have something like that. There's the voltage phasor, and what do we get for our current phasor? 13.3 at 90. So we ended up with our current phasor looking something like that. Okay, so in the phasor domain, we'll see the voltage leading the current, And there'll be other things throughout next term that we really use this phasor diagram for. It's probably a lot easier to look at things in the phasor domain than in the time domain. And hopefully I emphasize that again with that notion there. I don't want to have to go through this math when I could just use some phasor work. So it's worth looking at the phasor. Well, let me look at the final answer. I think we also came up with a final answer that I in phasor form, and I've noted these in phasor form here, that I in phasor form was equal to 13.3 at 90. And I think then we went back into the time domain. So in the time domain we had 13.3, and then I wrote it in terms of cosine, 377t plus 90. That was amps. And but remember, we had started with sine and had to convert that sine to cosine. Remember how we did that? We said that if we had the sine of theta, that was equal to the cosine of theta minus 90 degrees. Is that what we did here? We had the sine minus 90, so I subtracted another 90. That's how we got that minus 180, right? So it'd be kind of interesting. I mean, we could go back to cosine. I think that, I mean, we answered the problem and we did it well. This shows up well on the phasor diagram, but I guess just a final FYI on this. And if we wanted to, we could say that this was equal to 13.3, and then I would say the sine of 377t plus a 90. Now, how do I get from cosine to sine? It looks like I would need to add another 90. So I would say that this would be 13.3 sine of 377t plus 180. Okay. And then you could, if you really wanted to, you could take that 180, being 180 out, and end up putting that in front as a negative if you wanted to. Okay, so a lot of times you'll see things that may not necessarily match your answer, and that doesn't mean that they're necessarily wrong or that your answer is wrong. You may just have to convert them a little bit. So be careful of that. There is nothing wrong with our answers here. We did a fine job of that, but I just wanted to point out that additional thought there. Well, let me continue on. I've got a couple more problems that I'd like to tackle in this area. We last time did one with the resistor. We then did this one with the inductor, so it doesn't take much imagination to figure out which one's coming up next. That is one with a capacitor. So let's try this. So let's say that I have a circuit here. I have a capacitor where C is equal to 1 microfarad, and I've got this voltage across here, V of t, and I would like to come up with I of t. Okay, so that's what I'm trying to find. And we're going to say that the voltage is given as 10 cosine 377t minus 30. And this is actually a homework problem that you're going to be working on. I think it's a two-part problem. It has one voltage in cosine, it has one in sine. I'll do the cosine one. I'll make you do the harder one. Remember, that is very much like we did in this last problem. You'll take that sine expression and convert it to a cosine expression. So anyway, with this, if I'm looking for that current, I know that that current, at least in phasor form, is going to be equal to the phasor voltage divided by the impedance, right? I mean, that comes from Ohm's law. V is equal to I times R. So with that, let's see if we can get started. First of all, I need to put this into phasor form. So if I look at this in phasor form, I could say that this was, what, 10 at an angle of minus 30 degrees. That would be that in phasor form. Probably should say that this is volts. The other thing would probably be, I guess we maybe need a motivation for this. I mean, if I didn't do this, some people are saying, well, why do we have to do all this weird stuff with phasors? Well, if I didn't, what would we have? Well, we'd have something like this, where I have a V of t. I have the capacitance here. I've got the current I. And I could say, by the governing equation of that capacitor, that I is equal to C times dV of t dt, right? So you could get the current, but you'd have to take the derivative of that. So rather than taking a long trip down calculus and whatnot, I think there's some advantage in dealing with the phasors, and so does your author and most electrical engineers. So with that motivation, carefully segregate that. We don't want to do that. We want to use our phasors up here. What is Z for a capacitor? Well, we said that was J omega L. That was for an inductor. We had 1 over J omega C, which we said was also equal to minus J divided by omega C, right? We talked about that last time, how you got that J up into the numerator as a negative J then. You go back to last time's lecture if you're questioning that. So I could say that I have then minus J times 1 over omega C. Well, there's omega right there, so 377. And C is 1 times 10 to the minus 6. So what's this turn out to be? Minus J. So when I do that, I get 2,652.519. Let's call it 2653. Okay. That's actually ohms. 2653. Okay, so we've got that. We should be ready to go here then. We can say that I have 10 at minus 30 divided by a minus J and 2653. And once you get used to putting this into your calculator and whatnot, you can just tap this out fairly easily. And that would be a good thing to practice on over break, is doing complex numbers with your calculator. If you don't have a calculator that can do that, you should probably be able to finish up this term pretty well, but that's probably something you want to try and run down over the break if you're coming back and taking this class next term, is a calculator that will handle complex numbers. And some people ask, oh, how many complex numbers? Well, before we're done, we're probably going to do systems of linear equations with complex numbers. So if your calculator can do that, you're probably in pretty good shape. And most of you, I think, have calculators that can do that. Well, so what do we have here? We've got, then, if I go through this, I could say that I have minus J. Where's minus J? We'll go over to the real and the imaginary. Minus J is going to be down here, isn't it? Isn't that minus J? Yeah, that's minus J. So what's another name for that? I could say that was 1 at minus 90. Could I do that? 1 at minus 90? I think so. Okay, so I've got 10 at minus 30. And then I have this minus 1. Whoops, not minus 1. I could say minus 1 at 90, but I'll keep it. Yeah, we could say minus 1 at 90. That'd be an OR. But I'll take it as 1 at minus 90. And then I have this 2653. So what's this turn out to be? Turns out to be 10 divided by 1 times 2653 at an angle of minus 30. And then I subtract this, which is minus 30 minus a minus 90. So that's going to be a positive. Positive comes from minus a minus. So what do we come up with? So I have 3.77 at an angle of, well, actually I have something much smaller than 3.77, but I've converted this. This would be in amps because we have volts over ohms, right? Volts and ohms. So I multiplied it by 1,000, so I have milliamps. 3.77, then what would our angle be? 90 minus 30 is 60. Okay. So you'd have something like that, 3.77 at 60. So that's the answer in phasor form. I'll double check that with my notes. 3.77 at 60. Now, had you gone with this one right here, you would have come up with, what would you have come up with? You'd have had minus 3.77 at minus 120 milliamps. Is that the same? Now let's see. Again, going to the real and the imaginary. And I have 3.77 at 60. That puts me about right there, doesn't it? And so that was 60. If I go to 60 minus 120 takes me down to there, and then minus 3.77 puts me back up to there, doesn't it? So these really are the same. And again, we tend to lose negative signs, so this is certainly not the best answer. This is a better answer, although they are the same. If you can say that, them being the same, but one's better than the other. I'll let the philosophy people work that out. Anyway, I was given the problem in time domain, so I probably need to answer in time domain. So in time domain, I of t is going to be equal to what? 377 cosine. We were doing it based on cosine. No, 3.77. I got too many 377s. 3.77 cosine of now 377t, and then plus 60 milliamps. So that would be the answer in time domain. Let me double check my work here with my notes, make sure I haven't led you astray. Yeah. Okay. So, and again, I would say much easier than this approach here. Once you get used to this, you can do much of this in your head, and you get a calculator that's helping you out. And I don't want to use the calculator as a crutch, but once you understand how to do this, there's no need in going through a lot of this manipulation by hand. You just pop in your calculator, and away you go. Well, I want to try one more problem for today, and it too is a homework problem. A bit of a jump start on those. So let's say that we have a grouping of impedances, resistors, inductors, capacitors, like this. So I'll say that I have 1 ohm here, 10 microfarads, 2 ohms, 10 millihenries, and I look in here and I want to know what the impedance is. Okay, I'd like to know what the impedance is. Well, in general, I can say that the impedance for a capacitor, we saw that that was minus J over omega C, right? That the impedance for an inductor was J omega L, and of course the impedance for a resistor is simply just equal to R. If you want to be fancy, plus J0, right? Okay. So we've got that, and as I add these up, we're going to add these just like resistors. So as I'm going to combine like resistors or inductors. So maybe I'll note this. Okay. So we combine impedance We combine like resistors and inductors. And I say, well, what about capacitors? Well, you notice we've already flipped that. Okay, so even the capacitors in here, when I convert it into an impedance, I will combine them like resistors and inductors. So capacitors really do end up being the odd thing out. If you go back and someone just gives you all capacitors and you want to combine those without turning them into impedance, and then you do it the opposite of resistors and inductors. But if I've turned them into impedances, I'm just going to combine them just like resistors and inductors. So important point there. Well, I guess I need to give you a frequency here. We'll say if the frequency f is equal to 60 hertz. So we know then that omega is equal to 2 pi times f, so that's 377 radians per second. So I can, at that point, figure out what the impedance for the 10 microfarad, the impedance of the 10 microfarad is going to be minus j divided by 377 times 10 to the minus 6. Which gives me, what's that turn out to be? Run through that real fast. Not 265.25, we'll just say 265. So minus 265, the j. I really got, where did I get the, oh, the 2000 was from the last problem, wasn't it? Because what was it? It was 1, yeah, it was 1 microfarad. This is 10 microfarad. So that's why that stuck in my head. Anyway, let me tidy this up a little bit. Okay, so minus j, 265, and that would be ohms. Likewise, I could do the same thing or similar thing for the inductor. So Z for the 10 millihenry would be J times 377, J omega L. So L is 10 times 10 to the minus 3. So I come up with what, 3.77, I think? Yeah, I should. Yeah, so positive J, 3.77 ohms. And of course the resistors are just the resistors. So I can say then that my equivalent impedance is going to be equal to, these two are in series, right? Okay. So what's that going to be? I'm going to use this is really just 2 minus J 265. Okay. And that's in parallel with that, so I'm going to use product over sum. So I'm going to take 1 and I'm going to multiply it by 2 minus J 265, and I'm going to divide that then by the sum, which is 1 plus 2 minus J 265, and that takes care of everything to the right of this dotted line there. And what do I have to do? That's in series with that, so I'm going to then have to add, because it's in series. So I did product over sum because these two were in parallel, then I added because this is in series. I have to add for the inductor, which is plus J 3.77, right? And again, I would probably just at this point pop that in the calculator. If you don't have a calculator that can do that, you can run through the math here. What are you going to have? You're going to have 2 minus J 265 divided by 3 minus J 265 plus J 3.77. Is that right? How would you then do this division? Well, you're going to have to convert that to a polar form if you wanted to. What would that look like? You're going to have, you would go into, and I won't necessarily go through all of the pieces of this. A lot of you probably got this done with your calculator already. But looking at the real here and the imaginary, you're going to go 2. So there's 2, and then there's minus 265, and you're going to have this point down here. So you have to come up with the magnitude and angle, theta, and whatever the magnitude of this is. So you'll convert this to a magnitude 1 at some theta 1, and then you're going to have to do it again. And this is why you want to get a calculator that can do this, because it's get quite tedious. You'll have to do the same thing for the bottom, except now it's 3 at minus 265. So you have some magnitude 2 at some theta 2. Then you can divide the magnitudes and subtract the angles, and then you're going to have to convert that back to a rectangular to add it to that. I think with that, I'll throw it into the calculator and see what I get. Yeah, there we go. So we end up with 1 plus J 3.77, or that would convert to, that would be the rectangular form. You could convert that if you wanted to a polar form, which is which we answer it both ways. 3.9 at an angle of 75, and either one of these would be in ohms. Those would both be in ohms. Probably, if this is a voltage or a current, this would be a nice way to go, because we go right back into the time domain. If we have the impedance, though, oftentimes we'll have the answer like this, because this gives us the resistive portion. This whole thing looks like 1 ohm of resistance plus J 3.77. Actually, I think it's a little less than. I should remove this last 7 here. It's not quite that, this because of this leading term here. So I think that takes care of that. Gives you hopefully a head start on some of your homework problems. Let me double check my answers here. Yeah, 3.7. That would be degrees. So, like I said, hopefully this gives you a jump start on some of your homework problems, and covers hopefully a good introduction to AC analysis. We'll spend a lot more time. If you're wondering, well, how did we derive these? How did we come up with those? That's what we're going to start next term with. Well, the last lecture that I have to do in here, I want to take a fairly difficult problem and essentially do it as a review. I'm going to take kind of an ugly 6-step problem, not because we need to review more of 6-step problems, but 6-step problems tend to lend themselves to a lot of circuit analysis, mesh analysis, node analysis, equivalent resistance, things like that. So they're a good problem to do some review with. So I'll take a difficult problem of that, go through that as more or less a review, and that will wrap it up for the term. So thank you for watching. Take care till then.